So, solutions. What is a solution? A solution is a synonym for a more complex term called homogeneous mixture. And it essentially says that you got one uniform consistency or layer. And what's you find in a solution? Well, you got stuff that's dissolved, that's called the solute. And you got stuff that does the dissolving, that's called the solvent. So the solvent does the dissolving. Usually, there's more solvent thing that's dissolving than there is solute, but every once in a while you get a super concentrated solution where there's more stuff dissolved in it than things doing the dissolving, which is pretty crazy. So anyway, hopefully you got these three terms down: solution, solvent, solute. Um, how does a solution form? When you put a solute in a solvent, how does the solution get created? Well, it happens through a process called spontaneous mixing, which will make a little more sense when we get to the thermo unit. But essentially, three things need to take place when you dissolve something. Um, a solution, by the way, will spontaneously on its own over time uh, fill itself out to become a uniform consistency. So, for example, and this is just spontaneous on its own. If I have this, container with this divider in it, on one side is pure water, on the other side is a saltwater solution. If I remove the divider, over time, eventually the solute, the sodium chloride solute, will eventually just spread out so that this is of a uniform consistency. So it's not like once I remove this divider, it's not like this side will stay more concentrated than that side. And we could expedite that process by stirring it, but over time, even if you don't mix it or stir it, the particles, as they're in constant motion, they'll eventually move over there and it'll become a uniform concentration all the way throughout. When I add a solute to a solvent, how does it dissolve though? Here it's already dissolved, right? So how does it dissolve? Well, really it's a three-step process. And the first thing you have to do is you have to break apart the solute. So whatever intermolecular forces, and we'll get to intermolecular forces on Wednesday, whatever intermolecular forces, whatever forces are holding the solute together, if it's an ionic compound, that would be its lattice energy. Okay. Whatever forces are holding the solute particles together, you got to break those. So you got to put energy in to break the solute particles. And so we call that the enthalpy of the solute. And then you have to make room for the solute in the solvent. So the solvent particles, you got to break some solvent particles. If it's water, we'll talk about this Wednesday, that would be hydrogen bonding. So we have to break the solute apart. Then we have to cause the solvent, right, particles to move to make room for the solute. That's going to take energy. But when the solute and solvent mix and now form new interactions, we call that the enthalpy of mixing. That's going to release energy. So the first two steps of this three-step process take energy. We got to break the solute apart. That's called the enthalpy of the solute. We got to move some solvent particles. So we got to break a couple solvent-solvent interactions. That's going to take energy. But when the solute now fills in these holes and forms new interactions with the solute-solvent interactions, that's going to be the enthalpy of mixing. Okay. And this is what's going to determine whether or not when you dissolve a salt, whether or not it gets cold, whether or not it's an endothermic solvation, or if it gets hot, whether or not it's an exothermic solvation. So if you're a visual person, this might help. If the amount of energy needed to break apart the solute particles and move the solvent particles, if that is less than the amount of energy you get back when the solute and solvent form their new interaction, then you're going to have an exothermic solvation. So sodium hydroxide, for example, is like this. If I dissolve sodium hydroxide in water, it gets very hot. So it takes less energy to break apart the ionic bonds in the sodium hydroxide and to move some waters around, break some hydrogen bonds. It takes less energy to do that than the new interactions between the sodium and hydroxide ions in the water when you get back. So it's exothermic. Some salts, though, when you dissolve them, it gets cold. For example, I believe ammonium nitrate gets super cold. Why is that? Well, it takes more energy to break apart the solute and get the water molecules or solvent molecules to move. Then you get back when the solute and solvent form new interactions. So that's going to feel cold. It's going to be an endothermic process. So this explains why some salts make the solution hot when you dissolve them, and why some solutes make the solution cold when you dissolve them. So some types of solutions. We have really three types of solutions. You can have a solution that is unsaturated. What that means is that you can add more solute. The solution is not currently dissolving the maximum amount of solute. So you could add more solute and still get some to dissolve. That's what an unsaturated solution is. A saturated solution is one in which the solvent, is currently dissolving the maximum amount of solute. You cannot get any more solute to dissolve. A lot of times, a saturated solution will have a lot of extra solute sitting on the bottom. So, for example, let's say I have a beaker, okay, and there's my beaker, there's my water, and I add a whole bunch of sodium chloride to it. Well, at first, when I add the sodium chloride, it's going to dissolve, right? It's going to be unsaturated. But if I keep dumping sodium chloride in there, eventually it's going to dissolve the maximum amount of solute it can. And then the extra sodium chloride is going to sit on the bottom. So a lot of saturated solutions have excess solute sitting on the bottom here. And that's an easy way to tell. If you've ever had to make a brine in cooking or something, you just dump a whole bunch of salt in the water and shake it around and let it sit there overnight. And as long as there's still salt sitting on the bottom in the morning, you got yourself a saturated sodium chloride solution, right? And then there's a special type of solution called a supersaturated solution. And a supersaturated solution is crazy. A supersaturated solution is a solution that is currently dissolving more solute than it should be able to dissolve at that temperature. Supersaturated solutions are made by taking your solvent and heating it up, like on a hot plate. So you get a hot plate, you heat it up, and by heating the solvent up, in general, this is not a law, but in general, as temperature increases, you can get more solute to dissolve. So, for example, at higher temperatures, you might be able to get 90 grams of solute to dissolve in 100 milliliters of water instead of only 30 at room temp. So you heat the solvent up, you get a whole lot of solute to dissolve. And if you allow the solution to slowly cool back down to room temperature, the excess solute sometimes will stay dissolved. And then you end up with these crazy solutions. So let me show you a YouTube video here. Give me 1 second to pull this up. All right, so we got some supersaturated solution of sodium acetate here. What you did not see is that this individual heated the sodium acetate up, heated this solution up, got a whole bunch of sodium acetate to dissolve at really high temperatures. And then they let this thing cool back down. Now, I used to do this demo, but it is a pain. These things have a mind of their own. Supersaturated solutions are really unstable. If you bump them, sometimes just the act of picking up the flask causes it to freak out. So you can see here, this dude is going to pour this into this Petri dish. And just the act of pouring this thing out ticks the solution off so much. And it says, wait a minute, I am an abomination. At room temperature, I should not have this much solute dissolved inside me. And what it does is it just crashes out. So this is all the excess solute that was in there crashing out. It's seeding, crystallizing, and coming out of the solution. There, I can see my video cards freaking out. So now what he's going to do, this is called the pillar of salt demo. It's pretty awesome. I used to go into like elementary schools and do this and stuff. The dude is going to pour some more of the supersaturated solution out. The supersaturated solution is going to hit the solute that is now crystallized on here. And the solution is going to say, wait a minute, I already have too much stuff dissolved. Now you want me to dissolve more. And what's going to happen is if you pour this slowly enough, the excess solid crashes out as you pour it. So they call it the pillar of salt demo. This dude gets greedy, right? He's a pretty big tower of salt going here. Come on. There we go. he gets going, you know, he's pouring it, pouring it, pouring it, pouring it, and then eventually, boom. Now, these solutions have a mind of their own. This dude is going to pour this guy into here. And remember the last time that he poured it out, just the act of pouring it out agitated the solution enough to start to crystallize and kick out the excess solute. But this time it wasn't enough, right? So now what he's going to do is a process called seeding. He's going to grab some more solid sodium acetate from over here, one of his pillar of salt things. He's going to drop it in there, and that creates a nucleation site for the sodium acetate to start seeding out and crystallizing out. So super saturated solution, super cool, super crazy, and just, you know, what is an application of that? I don't know, right? But they're just super cool. And, you know, you may have never seen that before. So you got unsaturated solutions, saturated solutions, and super saturated solutions. Cool. All right. So solubility, why does it matter? Well, solubility tells you a lot. Remember with solubility, like, so how do you determine if something is going to dissolve? Well, we have a pretty simple way of doing that. We say like dissolves like. This is going to make hopefully a little more sense after Wednesday's class, where non-polar things tend to mix. So you can get a non-polar solute to dissolve in a non-polar solvent. And polar things tend to mix, so you can get a polar solute to dissolve in a polar solvent. And then, you know, like ionic is as polar as it gets. So salts tend to dissolve in polar things like water. So we got this like dissolves like. And there was a set of solubility rules from Chem 101, if you'll remember. There's a set of like 6 rules. We'll revisit that when we get to the equilibrium chapter. We talk about applications of aqueous equilibria when we get to the solubility product constants. Okay, so this graph is what I was just talking about here for the supersaturated solutions. And what you can see, this is a graph of the solubility of a solute in grams versus temperature. So what this graph tells you is how many grams of these solutes you can get to dissolve in 100 grams. Remember, water has a density of 1, so it's about 100 milliliters, right? Okay. So how many grams of these solutes can you get to dissolve in 100 grams of water? So imagine you got a beaker, you know, and you got the 100 mil mark, right? So you got that much water in there. This is going to tell you how many grams of these solutes you can get to dissolve at various temperatures. And the first thing I want you to notice is what I was saying earlier. Most salts become more soluble at higher temperatures, right? Look at potassium chlorate, solubility goes up. Look at potassium dichromate, solubility goes up. On this graph, there's only one exception. Sodium sulfate actually becomes less soluble. So this is not a law. This is a trend. Most solids become more soluble at higher temperatures. So if you want to get more stuff to dissolve, heat the solvent up, and you can usually get more stuff to dissolve. Now, sodium chloride, table salt, doesn't have a drastic change. Goes from like what, maybe 34 to 36, right? I mean, it's not grams per 100 mils. Not a big change there for sodium chloride. It's pretty stagnant. Some salts, you know, like calcium chloride, that would be a great salt to try to make a supersaturated solution out of because, you know, at room temp, you know, you can get room temps about 20 degrees. So room temp, you get like this much, you know. Potassium nitrate, another great one, room temp, and then heat it up a little, you can get a lot more to dissolve. So yeah, recrystallization, if you take organic chemistry, you'll learn about a lab technique called recrystallization. It takes advantage of this. So I'll let your organic professor talk to you about that. Hopefully, maybe this fall, who knows? Temperature of gases and their solubility. This is going to have the exact opposite trend. So this previous slide has talked about the solubility of solids, and most of the time solids become more soluble. But what about gases? So when I have a gas that's dissolved in a solvent, how does temperature affect its solubility? Well, this is the exact opposite trend. Gases are less soluble at higher temperatures. Okay, so for exam, this is a law, right? There are no exceptions to this one. This is a law. So, for example, opening cold soda versus warm soda. They both have the same amount of carbon dioxide dissolved in them, right? Because soda's carbonated. It's got dissolved carbon dioxide gas in there. When you open up the cold soda, the carbon dioxide is not as eager to get out. But when you open up the warm soda, that carbon dioxide wants out, right? You get a lot of foaming on that thing. Okay. If you're really into fishing, you know, fish, there's more dissolved oxygen in cold water. So on a hot day, you'll see the fish chilling in the shade, right? Because it's colder. You'll see them in deeper parts, right? Because it's colder down there. There's more dissolved oxygen when it's colder. Obviously, also, if you're fishing a river or something, the current, how aerated it is. If there's a lot of rocks and stuff, you'll have fish chilling in there because the oxygen's getting pumped in. But temperature also affects its shade. One of the best things you can do if you're trying to make a good trout stream is to have it be heavily shaded, because trout need a lot of oxygen. So the more shaded it is, the greater the chance. Around here, especially with it getting hotter and hotter, July and August is just too hot for the trout in the creeks and streams here in Lancaster County. We do have some native brook trout in a couple streams, but not many. And unfortunately, a lot of times farmers will farm right up to the edge of the stream and they cut down the trees and stuff, and there's no shade, and now there's not enough oxygen to support trout. Maybe smallmouth bass, but not trout. They need a lot of oxygen. Okay, so here we got some Henry's Law, folks. Henry's Law allows us to predict the solubility of a gas. Okay, you're going to want to write this formula down. It allows you to predict how much gas you can get to dissolve the solubility of a gas by setting it equal to some constant called the Henry's Law constant times the partial pressure of the gas above the liquid when it's like when it's being bottled or something. So for example, if I want to calculate the solubility, like how much carbon dioxide is dissolved in a soda can, if I know the Henry's Law constant for carbon dioxide and water, and I know the partial pressure, how much pressure of carbon dioxide they applied to this before they sealed the can, then I could determine the solubility. Or vice versa, if I know the solubility, okay, and the Henry's Law constant for carbon dioxide and water, I could calculate what the partial pressure has to be able to achieve that. What pressure of carbon dioxide do I need to have? So I actually worked it out. This is a real world problem here for you folks. The concentration of carbon dioxide in most carbonated beverages is about 0.12 molar, 0.12 moles per liter of carbon dioxide dissolved in there. Obviously, sometimes, if the soda is old, some of the carbon dioxide has escaped. Obviously, I don't know if you've ever had like a fountain soda where it wasn't working right, and it was like super fizzy. And some sodas now, they market themselves as being super fizzy, so they just bottle it with more carbon dioxide. But anyway, I would actually like to calculate the partial pressure of carbon dioxide. If most sodas are 0.12, what must the pressure of carbon dioxide be when they bottle that soda? Now, in order to do this, we're going to need the Henry's Law constant, which we're going to need this chart here. So this is a chart of the Henry's Law constant of various gases in water at about room temperature, 25 degrees Celsius. It's a little warmer than room temp. Room temp is usually about 21, 22 degrees Celsius. Depends where you are. So the Henry's Law constant for carbon dioxide in water at about 25 degrees Celsius is 3.4 times 10 to the negative second molar per atmosphere. So it's got weird units. You're going to see why. Give me a second. I'm going to write this information down. I'm going to write that formula down, and we are going to solve for this bad boy. Let's do this. So here we're solving for the partial pressure of carbon dioxide. Now, I'm an algebra up front kind of guy. So right now, this formula is set up to solve for solubility, but I have the solubility. I want the partial pressure. So I'm going to divide both sides by the Henry's Law constant. And the partial pressure of the carbon dioxide is equal to the solubility of the carbon dioxide divided by the Henry's Law constant. So we're going to pop that solubility in there, 0.12 molar, and then we're going to divide by that Henry's Law constant, 3.4 times 10 to the negative second molar per atmosphere. Notice molar cancels out. And notice that atmospheres is in the denominator of a denominator, and the denominator of a denominator belongs in the numerator. So we're going to get a partial pressure in atmospheres here. So 0.12 divide, whoop, got to turn my calculator on first. 0.12 divided by 3.4 e negative 2. This is 3.5 atmospheres of pressure. So when they bottle like a soda, like a can of Coke, right? When they bottle that Coke, they get the Coca-Cola in there, and then they apply 3.5 atmospheres of pressure worth of carbon dioxide in there, and then they seal the can. And then that 3.5 atmospheres of carbon dioxide forces itself into the solution, and that's how you get the carbonation, right? The carbon dioxide is dissolved. And then when you open it, now it goes, right? And now it's at 1 atmosphere of pressure. So this carbon dioxide starts bubbling and fizzing and trying to escape because it's not being held in there anymore. It's not being forced in there. So there's your Henry's law problem, okay, for solubility of a gas in a solution. Awesome.